going to discuss the convergence of beta and gamma function. So for that, we are going to see some test. Particularly, we are going to see the mu test. So let me write the definition or the mu test. Mu test. So this mu test is for your improper integral of first kind. Let me write it. IMPROPR, improper integral of first kind. Okay, so obviously there is a mu test for improper integral of second kind, and then we require this both mu test. Okay, so let me write. So let fx be bounded and integrable for the interval, or in the interval पनि भन्दा हुन्छ, for the interval a comma infinity where this a is any positive number. Okay, so now I'll say this mu test, this value of mu. So if there is a number mu which is greater than 1, okay, so if there is a mu which is greater than 1 such that my limit x tends to infinity x to the power mu, okay, we are multiplying this x to the power mu with that function fx exists. If this exists, then we say the improper integral 0 to infinity fx dx is convergent. Okay, so अर्कोमा हेर्दाखेरि, so if there is a number mu which is less than equals to 1. Now just the opposite, if we find in mathematical condition satisfy गर्दैछ, but then the mu is less than equals to 1 such that my limit x tends to infinity x to the power mu fx exists, then my integration fx dx is divergent. Okay, so it is going to be divergent. Also in the case when this limit, if it is also for my limit x tends to infinity x to the power mu fx is plus minus infinity, or whenever we get the value of the limit that we are going to calculate as plus infinity or minus infinity, at that point also we say this is divergent. Okay, so we have completed the mu test for improper integral of first kind. So now we are going to see another mu test for, this is for improper integral of second kind. Okay, so improper integral of second kind, and then whatever we saw before, it is just going to be the opposite of what we have done for the first kind. Okay, that means whenever the value of mu is between 0 and 1, we say the integral is convergent. So whenever the value of mu is greater than equals to 1, we say the integral is divergent. Okay, so let me write the definition here. So also this, for this case, our fx has to be bounded. Let fx be bounded and integrable in the interval my a comma infinity. Okay, so obviously it is of second kind, that's why obviously there will be a point where the function will not be defined. Okay, so we'll take that point to be a, so that's why we will be introducing some other factor to replace that. So as we have done in our second kind, a plus epsilon infinity. Okay, so 0 is less than epsilon is less than b minus a. Okay, so I will just ignore the sound. Obviously for this mu test, what we are going to do, as I have already told you, so first condition will be again in this case we are going to remove the discontinuity by subtracting the value from the x. Okay, so first condition, what we'll write, if there is a number mu 0 is less than mu is less than 1 such that my limit x tends to a plus 0. Okay, wherever there is a point of discontinuity, or we say the function is not defined at that point, so we'll take that point a, x will tend to a. In previous case, x was tending to infinity. Okay, so in this case, x will tend to a. So from the right side, so we are taking this, so it is going to be x minus a to the power mu fx exist. So if this exists, then we say the integration fx is convergent. Okay, so then my integration 0 to infinity fx dx is convergent. Okay, so it converges absolutely. So absolutely convergent, any integral is also convergent, so we'll write converges absolutely. So it's a stronger case. So number B, so if there is a number mu which is greater than equals to 1, such that my limit x tends to a plus 0, so x minus a to the power mu fx exists, then I can say 0 to infinity my fx dx is divergent. Okay, so and also, as I have told, whenever the limit is plus or minus infinity, and the same is true if my limit x tends to a plus 0, x minus a to the power mu fx equals to plus minus infinity. So in case the limit is either infinity, plus infinity, or minus infinity, at that point also we say that the improper integral is divergent. Okay, so now let us see, let us try to prove. Question is, we'll check the convergence. So check the convergence of gamma function. Okay, so question is asked in this way only, and then this is the most asked question in your end semester examination. So we know solution. So we know what is gamma of n, right? Gamma of n is the integral 0 to infinity e to the power minus x, x to the power n minus 1 dx. So this is the definition of gamma function, and then we want to check the convergence of this gamma function. Okay, so obviously we have a term n, so this n might vary, right? So for us n might be greater than equals to 1, or it might be between 0 and 1, and then it might be less than equals to 0. Okay, so let us do some cases. So obviously I'm considering 3 cases. So in first case, I'm taking n is greater than equals to 1. Okay, so if my n is greater than equals to 1, so let us see whether this function has a discontinuity or not. It has no discontinuity when n is greater than equals to 1, because as you can see, my x to the power n minus 1, here we have, let me do some rough. So we have x to the power n minus 1. So my n is greater than equals to 1. That means this term is going to be 1 by x, because n can be anything, right? It is greater than 1, so it is always, sorry, not in this way, this n is going to be greater than 1 when you see it is getting subtracted from 1, so it is always going to remain in the upper side. Okay, it is always going to remain in the numerator side, so we have no problem with this. That means it is bounded also, it is integrable also. Okay, so it has no point of discontinuity. But then in case of n less than 1, we can see that this part is going to be 1 by x to the power n. Okay, because this is less than 1, that means this whole term is going to be negative. In that case, it is going in the denominator part, and then we see a discontinuity at x equals to 0. That means the function is not defined at x equals to 0. Okay, so let me come back. So for case 1, if n is greater than equals to 1, we are going to say our fx is e to the power minus x, x to the power n minus 1 is bounded and integrable. Okay, so it is bounded and integrable, but then it is an improper integral of the first kind. So obviously we are going to find, we'll try to find a number mu which will help us to see whether this is convergent or not. Okay, so let me check the value when x tends to infinity, x to the power mu e to the power minus x, x to the power n minus 1. This is going to be, so limit x tends to infinity, x to the power mu plus n minus 1 e to the power minus x. Okay, so this is the thing that we have here. Now let us see. Okay, so I can take this e to the power minus x in the denominator part, and then we know the binomial expansion of e to the power x. Okay, so let me write the binomial expansion. So limit x tends to infinity, x to the power mu plus n minus 1, this is 1 plus x square by 2 factorial plus dot dot dot, it goes on. Okay, so now as we move further, this is the denominator part is increasing as we move further, right? So obviously it is going to be 1 by infinity. Looking at this, so this limit is going to be 0. So obviously this is going to be for all values of mu and n. Okay, so since it is going to be true for all values of mu and n, and we got a finite value that is 0 over here. So what we can take, we can take mu to be greater than 1 for this case. Okay, and then by mu test for improper integral of this side, I don't know why it's not writing. So first kind, what we can claim is this improper, because we got a value that is mu, it is greater than 1, right? So for first kind, mu test for first kind, we have this is convergent. Okay, so implies my integration 0 to infinity e to the power minus x, x to the power n minus 1 dx is convergent for all values of n. Okay, that means for we are taking the first case, we are taking for all n greater than equals to 1. Okay, so for second case, so case 2, so in case 2, let us take the middle part, that is we have done for n greater than equals to 1. So second we are going to take for n which when it lies between 0 and 1. Okay, so as we see our n lies between 0 and 1, so in this case my fx that is e to the power minus x, x to the power n minus 1, so obviously it has infinity at x equals to 0 because my n is less than 1. Okay, it is less than 1 but then greater than 0. So what we have on the here, we'll get something like x to the power 1 by n, because my n is less than 1. So if it is less than 1 and then we have minus 1, obviously the output is going to be negative, so it is going to the denominator part. So in that case, if I take n tends to 0, sorry, x tends to 0, we get 1 by 0, that is infinity. Okay, so we have a discontinuity at the point x equals to 0. So the function is not defined at that point, so we have one discontinuity for this point. So it has infinity at x equals to 0. Okay, so now since the function fx has discontinuity, so what we are going to do is we are going to split the interval. Okay, so interval in the sense we are going to split the limits. Okay, so we have 0 to infinity e to the power minus x, x to the power n minus 1 dx. So let us split, we want to isolate the part where the integral is of second kind, and then we'll do the rest interval will be of the first kind, and then we'll follow the same procedure that we have done for case 1. So in this case obviously it is continuous because it is integrable. So for integrable function, what we can do is we can split the intervals. Okay, we can let us split 0 to infinity in middle, that is we'll take some point a in the middle part. So e to the power minus x, x to the power n minus 1 dx plus integration a infinity e to the power minus x, x to the power n minus 1 dx. Okay, so this is possible because the function is integrable. Okay, so now we have splitted the interval, that is I have taken integration from 0 to a, and then again we have to maintain the continuity, so a to infinity. So let us take the first part. Okay, so for the first part, let us take in a to 0 to a. Let us take 0 to a because we know 0 is contained in this interval in this limit, so it is of second kind. Okay, so this is of second kind, this is of first kind, because we have removed the discontinuity from the second part. Okay, so 0 to a, we have e to the power minus x. Obviously we have to do these separately, so we have this. Let us consider, so let me rewrite this. So let us consider this. Okay, so here this is the improper integral of the second kind, so obviously we are going to make use of the mu test of the second kind. Okay, so by using mu test for improper integral, I am writing short abbreviation, improper integral for of second kind, okay, so we have, this is going to be limit, we have the discontinuity at the point x equals to 0, so obviously x will approach 0. Okay, from the right side we are just looking at the right limit, 0 plus, so we will not write that though. So x minus 0 to the power mu fx equals to, so we let us put the value of fx, so x tends to 0, so this is going to be x to the power mu, so e to the power minus x to the power n minus 1 equals to, so let me write this. So this is going to be limit x tends to 0, x to the power mu plus n minus 1 e to the power minus x. Okay, so now we want to check its convergence, so let us assume this limit is going to be 1. Okay, we will not assume this, but then it is going to be 1. We want to make the limit point as 1. Okay, so why, because we want to check the convergence. Okay, so the limit has to be finite for that, so I'm taking the limit to be 1, but then it is possible, 1 is possible, because if I take e to the power minus 0, anything to the power 0 is 1, so exponential part is going to be 1, and then 0 to the power something, we do not know anything about that, right? So 0 to the power something is 0, it's going to be 0, but then we want to make it 1. So what we are going to do is we are going to make this 1, so x, so 0 to the power 0 is 1, so what we are going to do, mu plus n minus 1, it is only possible if the power of x is going to be 0. So in that case we can say the limit is going to be 1. Okay, so we could have taken 0 also, it is not a problem, because the value has to be finite, but then we are taking it to be 1. So if this is true, for the if you had taken 0, then we could not have known the value of mu and n, so it is necessary for us to take the limit value to be 1. Okay, so if this is the case, then I'll get the value of mu implies my value of mu will be 1 minus n. Okay, so it is going to be 1 minus n. Now what do we know about n? Okay, so we know n lies between 0 and 1. Okay, so we are subtracting n from 1, so n lies from 0 to 1, that means our mu will also lie, implies mu will also lie between 0 and 1. So 0 and 1, now we have the mu test for the improper integral of second kind. Okay, so the improper integral of second kind, what we have seen is this integral is going to be convergent. Okay, because whenever we have a value mu, and then if the limit exists, obviously we have made it such a way that the limit exists and it's equal to 1. Okay, so and the value of mu lies between 0 and 1, then we say the improper integral of second kind is convergent. Okay, so implies my integration 0 to a, sorry, e to the power minus x, x to the power n minus 1 dx is convergent. Okay, so obviously this is true by the mu test for the improper integral of the second kind. Okay, so now let us see the second part. Okay, in second part what we have is, now we have a to infinity e to the power minus x, x to the power n minus 1 dx. Okay, so now what we had done in case 1, so by case 1, so this integral infinity e to the power minus x, x to the power n minus 1 dx is convergent for all values of n. Okay, so it is convergent for all values of n, so this will imply my integration a to infinity e to the power minus x to the power n minus 1 dx is convergent. Okay, so in case 3 we have n is less than equals to 0. Okay, so let us consider this case. So in this case what we're going to see, we have the integral 0 to infinity e to the power minus x to the power n minus 1 dx. Okay, so now n is less than equals to 0, so we have the term that is x to the power n minus 1. Now n is less than 0, that means this term is always going to be written in this way. Now we have a discontinuity at 0 as well. Okay, so right, so this fx has this continuity at x equals to 0. Okay, and discontinuity, or you can say infinity at x equals to 0. Okay, at x equals to 0. So now obviously again we will split the integral into two parts. So one is, suppose let me write this to minus x to the power n minus 1 dx equals to integration 0 to e to the power minus x to the power n minus 1 dx plus a infinity e to the power minus x to the power n minus 1 dx. Okay, so now obviously in this case also we have the first part is of second kind and this part is of first kind. Okay, because it is excluding 0. So now let me do it for this again, dx. So here if I take limit x tends to, because here also we have the discontinuity point as 0, so x minus 0 to the power mu e to the power minus x to the power n minus 1 is going to be limit x tends to 0 x to the power mu plus n minus 1 e to the power minus x. Okay, so again we want to make this as 1, so this is only possible if mu plus n minus 1 equals to 0. Okay, so again we get the same value for mu, which is mu equals to 1 minus n. Now for us my n is less than equals to 0. Okay, so that means my n is always going to be negative or 0. So that means what will be the value of my mu? So mu for n equals to 0, it is going to be 1. Okay, so obviously 1 is there, and then if I take any negative number, there is a negative sign before n, so it is always going to make it positive. That means it is always going to be greater than equals to 1. Okay, okay, for n less than equals to 0. So by the improper integral, so mu test, okay, of improper integral of second kind, what we can say about this, because for mu greater than equals to 1, what I told on the improper integral is going to be divergent. Okay, so 0 to infinity, let me write e to the power minus x to the power n minus 1. Okay, this part I don't know why it's not writing properly. Let me move it a little bit slightly. X to the power n minus 1 dx is divergent for n less than equals to 0. Okay, so why I'm claiming it to be divergent, because what we have shown here on the this first part only I'm showing it is divergent. Now divergent, even if this is convergent, okay, even if the second part is convergent, we say obviously it is a sum of divergent plus convergent, so eventually this is going to be divergent. Okay, so we do not need to show the other part. So first part, if it is divergent, then the whole integral is going to be divergent. So we are claiming, because we found one of the integral is divergent, so the overall integral is also going to be divergent. Okay, so with this we have shown the convergence of gamma function. Okay, where we saw in the first case, when we have taken n is greater than equals to 1, the improper integral is convergent for all values of mu and n. Okay, so and then in second case we took the value of n to be in between 0 and 1. Okay, and in that case also what we saw is, we saw that the value of the integral is convergent. Okay, and then in third case, what we saw is we saw that for value n less than equals to 0, in this case the improper integral is going to be divergent. Okay, so the gamma function is only divergent for n is less than equals to 0. So with this I'd like to end my lecture. Thank you. In the next lecture we are going to see the convergence of beta function. Okay, so now we are going to see the convergence of beta function. Okay, so obviously this is going to be quite easier than what we have done before. So in case 1, what we are going to see, because you can see this beta function depends on m and n. So let us consider when my m and n are both greater than equals to 1. Okay, so the integrand is going to be finite. Okay, so it is going to be finite for all values of x from 0 to 1. Why is it so? On the head you can see, because my m is going to be positive and is also going to be greater than equals to 1, so it is always this x to the power m minus n, 1 minus x to the power n minus 1 is always going to be in the numerator part. Okay, so it's not going to be something like this x to the power m minus 1 and so and so. Okay, so it's not going to be in the denominator part, so obviously the integrand is going to be finite. Okay, so because of this, now what we claim is it is going to be convergent, because we know its limit is always going to be finite, because it lies x value of x lies between 0 and 1, so it is convergent. So we do not have to do a much in this case. So in case 2, so let us see when our m and n are both less than equals to 1. Okay, so less than 1. So then the integrand has infinities at x equals to 0 and x equals to 1. So let us see this infinities. So if my m n, so we have fx as x to the power m minus 1, 1 minus x to the power n minus 1. So what I'm saying, Mandahari, m is less than 1. So in that case, this is going to be x to the power m minus 1, and then my n is going to be less than 1, so it is also going to be something like this. Okay, so let me take this new parameter p and q. So pq, so obviously m minus 1, so if I subtract, it is less than 1, but it is going to be negative, so it will go in the denominator part. This is also going to be in the denominator part, so both is going to be in the denominator part. So for this, for x equals to 0, this is going to be 1 by 0, which is infinity. Okay, so obviously this is not going to be 0, so this is 1 minus 0, so it is 1. So for x equals to 1, so this is going to be 0. Okay, so this is going to be 0. So we have two infinities. Okay, so when x equals to 0, this part will act as 0, so it is going to be 1 by 0. So when x equals to 1, this part is going to act as 1 by 0, so it is going to be infinity. So we have two discontinuity for this function fx when x equals to 0 and x equals to 1. So we are going to again split the intervals, so we'll get two improper integral in this case. So let me write. So we have 0 to 1, x to the power m minus 1, 1 minus x n minus 1 dx, which is equals to, so let us split the integral. So this is x to the power m minus 1, 1 minus x n minus 1 dx plus integration a to 1 x to the power m minus 1, 1 minus x to the power n minus 1 dx. So as you can see, I have splitted the interval. Can you split garego bandahari, because we have discontinuity at that point. Okay, so we want to separate the functions. So for this, it has discontinuity at x equals to 0. For this, it has discontinuity at x equals to 1. So we have two second improper integral of the second kind. Obviously this a is going to lie between 1 and 0. So first let us see 0 to a x to the power m minus 1, 1 minus x, n minus 1, so dx. So this is the improper integral of the second kind, and then we have fx as this. So let us directly check the limit, and then discontinuity is at discontinuous, or I can say infinities at x equals to 0. Okay, so x minus 0 to the power mu fx for us is x to the power m minus 1, 1 minus x, n minus 1 dx. Okay, so this is going to be, so limit x tends to 0, x to the power mu. Obviously let us club this all in, minus 1, so 1 minus x to the power n minus 1. Okay, so I have written dx here, it is not required. So this is the case for this. Okay, so again I want to make this in limit finite. So if I put x equals to 0, this is going to be 1, 1 to the power anything is 1, so it is always going to give us 1. Okay, so now whenever I put x equals to 0, so for this I want to make this whole limit as 1. So what I have to do is I have to put this 0 to the power 0, so I have to make this, so this is only possible if my mu plus m minus 1 is going to be 0. So for this my value of mu is going to depend on 1 minus m. Okay, so now if, okay, so now we have, because this is the second case where our m lies between 0, okay, it is less than equals to 1, so I'm taking m to be between 0 and 1. So what we are going to have, we have, obviously my mu is also going to lie between 0 and 1. Okay, so and because my m, as you can recall, my m is going to be less than 1. Okay, so whenever it lies between 0 and 1, so this is the case, my mu is going to also lie between 0 and 1, and when my m is going to be less than equals to 0, so if I take m to be less than equals to 0 over here, see my m is already having a negative sign, so for m less than equals to 0, for 0 my mu is going to take value 1, and then for all negative values it is always going to be positive, so my mu is going to be always greater than equals to 1. Okay, so hence by mu test for improper integral of second kind, मेरो के हुन्छ यो not limit, as you can recall, mu test for improper integral of second kind मा चाहिँ हाम्रो mu को भ्यालु 0 र 1 मा हुँदाखेरि चाहिँ के हुन्छ, कन्भर्जेन्ट हुन्छ, र ग्रेटर देन इक्वल्स टु 1 हुँदाखेरि चाहिँ डाइभर्जेन्ट हुन्छ, भनेपछि यो केसमा डाइभर्जेन्ट, यो केसमा कन्भर्जेन्ट. ओके, सो kind मेरो integration 0 to a fx dx is convergent if my 0 is less than m is less than 1, because यो केसको लागि my this is going to be mu is going to lie between 0 and 1, and is divergent if my m is going to be less than equals to 0. Okay, obviously similarly we also have to check for the values of n. Okay, so similarly for the other integral, that is my a to 1 fx dx, what we have for this is infinity at x equals to 1. Okay, so limit x tends to 1, x minus 1 to the power mu, so 1 minus x to the power n minus 1, x to the power m minus 1. Okay, so I can rewrite this, limit x tends to 1, so I can take minus common from here, so this is going to be n minus 1, so 1 minus, sorry, let me rewrite this, it's going to be x minus 1, so mu is already there, and then this is also going to add up, x to the power m minus 1. Okay, so again I want to make the limit value as 1, so this is only possible if my mu plus n minus 1 is 0, so which gives mu equals to 1 minus n. So again the same condition as before. If my n lies between 0 and 1, we have my mu also lies between 0 and 1, because if I take n to be 0, it is mu is going to be 1. When my n is 1, it is going to be 0. When you see mu is also going to lie between 0 and 1 when I put the maximum values. Okay, so if my, so for this obviously the proper integral is going to be convergent. Okay, so now if my n is less than or equals to 0, again the same thing, my mu is going to be greater than or equals to 1. Okay, because you can see n has a negative sign on it, so whenever I put anything that is less than 0, it is going to be positive. So by again the mu test of improper integral of second kind, what I can say is this improper integral, okay, so a to infinity fx dx is convergent for n 0 1, okay, and is divergent for my n less than or equals to 0. Okay, so from case 1 and case 2, what we see, because it has the same result, right? So it follows 0 to 1 fx dx is convergent if both m and n are greater than 0 and is divergent if it is less than 0. Okay, so with this we end the convergence of beta function. Thank you.